So the reaction we'll be going over today is hydroboration. So this reaction is relatively straightforward. So essentially, you're going to have an alkene or a molecule for double bond. You can react with a borane, BH3, and then you're going to oxidize that borane, the hydrogen peroxide, and the sodium hydroxide for the second step. So essentially, for the end product, what you're going to have is you're going to add an OH and a hydrogen in addition, like that. And the OH is always going to be added anti-carbon carb, or in other words, the OH or the hydroxyl group will be added to the least substituted carbon or to the carbon that has more hydrogens. And the OH and the hydrogen will be added in the cis formation. So they can either be added both on a wedge, or you can also have it enantiomer, and that you have it added as the dash. So if you were to look at the transition state for this reaction, we draw this alkene. First step, BH. Okay, so the first step, which is a transition step, so it happens relatively quick, is you can have a box intermediate. So you got hydrogen that's attached BH2. So one of those hydrogens that's attached to that borane molecule is shown here. So you have the hydrogen on the left, you have the BH2 on the right, on the least substituted or anti-carbon carbon. And what's going to happen is with that second step, so second step, get hydrogen peroxide and the sodium hydroxide. The hydrogen peroxide and sodium hydroxide will oxidize that BH2 into creating a alcohol group, which was shown on that last problem. So again, you have the hydrogen on that carbon composition, then you have that OH right here. You also get its enantiomer. OH, H. And the reason the cis addition is because when you add it, or during the transition step, it's added that box mechanism. So that hydrogen and that BH2 gets added on the same plane. So that's why we have the OH and the hydrogen on the same face or on the same plane.